Think of a function as a small machine within a factory. It is designed to perform a specific task. In programming, a function is a collection of statements that execute particular operation. By breaking down a complex program into smaller modules, it becomes easier to manage, debug, and update. Imagine trying to find a needle in a haystack versus a small pile of hay. So when you have well-defined functions, you can reuse them across different parts of your program or even in other projects. This saves time and effort, making the development process more efficient. On the left side, this program has one long complex function containing all of the statements necessary to solve a problem. In this approach, all the logic and the statements need to resolve a problem are crammed into one long function. While it may accomplish the task, it's like having a Swiss Army knife with too many tools. It becomes unwieldy and difficult to manage. If something goes wrong, you have to sift through a large chunk of code to identify the issues. You cannot easily reuse a part of the code for another task, and the future updates or changes become a nightmare. On the right side, the problem has been divided into smaller problems, each of which is handled by a separate function. So the problem is divided into smaller, more manageable sub-problems. Each sub-problem is tackled by a separate function. The advantage is if any issue arises, you can isolate it to a specific module. Functions created can be reused in other parts of the program or even in different projects. Changes can be made to one module without affecting the entire program. Understanding the difference between a function call and a function definition is important for effective programming. Function definition, this is the blueprint of your function. It specifies what the function does when it's called. Think of it as a recipe for a dish, outlining the ingredients and the steps to cook it. The function call is the statement that triggers the function to execute. It's like telling the chef to cook the dish based on the recipes. The function call uses the blueprint provided by the function definition to perform a task. When defining a function, there are several key components to consider. Return type. This specifies the data type of the value that the function will return to the part of program that called it. Name. This is the identifier for the function. Function names follow the same rule as variable names, which generally means they should be descriptive and not start with a number. Parameter list. These are the variables that will contain the values passed to the function when it is called. Parameters act like placeholders for the actual values. Body. This is where the magic happens. The body contains the statements that perform the function's task and enclosed in curly braces. We have seen main function. Every C++ program needs a main function. For this main function, the return type is integer because at the end, the statement says return 0. 0 is an integer. The function name is main, and for the parameter list, inside the round parentheses, it's empty right now. The function body has two statements. The first statement is a cout, hello world, and the second statement is return 0. Integer main, then round parentheses, is the function header. If a function is designed to return a value, you must indicate the type of that value. This is known as the function's return type. Integer main function In this example, the main function returns an integer value indicated by int before main function. Function doesn't return a value. If a function doesn't return a value, its return type is void. This means the function performs an action but doesn't send any value back to the part of the program that called it. So in this example, we have a void print heading, and we have inside the body, we have a cout statement. Here, print heading doesn't return any value. It simply prints monthly sales to the console. The return type is void, indicating that no value will be returned. To invoke a function, you use the name followed by parentheses and the semicolon. Here, print heading round parentheses semicolon is a function call that triggers print heading function to execute. Once a function is called, the program's control jumps to that function, and the statements inside the function body are executed. So when print heading is called, the program prints monthly sales to the console. Once the function has completed its task, the control returns to the point in the program where the function was called, and the execution resumes from there. Let's walk through a simple program to understand how function calls work in practice. The program contains two functions, main and the display message. Main function is the entry point of the program. Execution starts there. Display message, this function displays a greeting message. First, hello from main is printed. Then display message is called. Control jumps to display message, and the hello from function display message is printed. After display message finishes, control returns to main function. Finally, back in function main again is printed. So main and the display message are both function definitions. Display message is a function call. Cout hello from main and the other cout statements are part of the function bodies. Function call like display message transfer control to the called function. Once the called function completes its task, control returns to the calling function, resuming execution from the point of the call. The main function can call any number of functions, not just one. This allows you to create complex programs by combining various tasks. Functions are not limited to being called from main. They can also call other functions. This is known as a function nesting. Before a function is called, the compiler must know specific details about it. These are usually provided in a function prototype or are defined before the function is called. So the compiler needs to know the name of the function, its return type, the number of parameters, so how many arguments in the function takes, the data type of each parameter. When working with functions, it is essential to notify the compiler about a function before calling it. One straight way is to define the function before it is called in the code. So this way, the compiler knows about the function when it encounters the function call. A function prototype can also be used. It is like a function definition, but without the body. It informs the compiler about the function's signature, including its name, return type, and the parameters. This is the function prototype. It tells the compiler that there's a function named print heading that takes no parameters and returns void. Note we have a semicolon at the end of the function prototype. Let's examine a program that uses multiple functions and the function prototypes to demonstrate the flow of program execution. Void first and void second are function prototypes. They inform the compiler about the existence and the signature of these functions before they are called in main. The function starts in main and it displays I'm starting the function main. It then calls first, jumping to that function and displaying I'm now inside function first. Next, it calls second, displaying I am now inside function second. Finally, control returns to main and back in function main again is displayed. Void first and void second are defined after the main function. Because we used prototype, the compiler knows about them even though they are defined later in the code. Function prototypes allow for flexible code organization, enabling to define function after they are called. The program's control flow moves from main to first, then to second, and back to main, demonstrating how functions can be called in sequence. It's a good practice to place all function prototypes near the top of your source file, usually right after the # include directive. This makes it easier to see what functions are available in the program. Before calling a function, the program must include either a prototype or the full function definition. Failing to do so will result in a compilation error. When using prototypes, you have the flexibility to place the function definitions in any order within the source file. The compiler already knows about them thanks to the prototype. Always include function prototypes near the top of your program for better readability and organizations. Ensure that a prototype or full definition exists for every function you call to avoid compiler errors. The use of a prototype allows you to define functions in any order in your source file, offering greater flexibility in code organization. You can pass values into a function when you call it. These values are known as arguments. Here we have a C equal POW, that's a power function, A, and we pass arguments A and B. A and B are arguments passed to the POW function, which returns A raised to the power of B. These are the actual values you pass to a function. They can be variables, constants, or expressions. Parameters are the variables inside the function definition that hold the values for the argument passed in. They act like placeholders for the actual value and are used within the function to perform its task. Arguments are the values you pass into a function at the time of the call. Parameters are the variables inside the function that receive these values. The function displayValue is defined to take one integer argument, which is represented by the variable num inside the function. In this example, num is a parameter. It acts as a placeholder for any integer value that will be passed to the function when it is called. The parameter num accepts any number integer value passed to the function and uses it within the function body to display the message. The value is the value stored in num. This program demonstrates a function with a parameter. The function prototype void display value int informs the compiler that there will be a function named display value that takes an integer parameter and returns void. This program starts in main and announces that it will pass 5 to display value. It then calls display value 5, passing 5 as an argument. Control would then move to display value where 5 will be used. The function definition for display value will be shown in the next slide. After the body of a display value is executed, the control returns to main and the program announces that it's back in main. Display value 5 is a function call where 5 is the argument passed to the function. Inside display value, this value will be stored in parameter. When main calls display value 5, the control moves to display value function. The value 5 is stored in num, and the value 5 is displayed. Control then returns to main. Inside the function, the parameter num holds the value passed as an argument during the function call. The function then uses value to display. The value is whatever stored in num. The void return type indicates that the function doesn't return any value. Again, inside the main, when we make a function called display value 5, and the control will go to the function definition, and 5 will be passed to the parameter num. When the statement cout in the display value function finish execution, the control will go back to the main function, resuming the statements after this function call. Parameters are also known as a formal parameter or formal argument. This is the variable declared inside the function definition. It acts as a placeholder for the value that will be passed into the function. In the void display value integer num, so num is a formal parameter. Argument is also known as an actual parameter or actual argument. This is the specific value or variable that you pass into the function when you call it. In the function call display value 5, so the number 5 is an actual argument. The prototype must include the data type of each parameter inside its parentheses. So here the prototype for even or odd specifies that it takes one integer parameter and the function doesn't return anything, it's a void. The function prototype must be ended with semicolon. For header, the part of the function definition, it must also include a declaration for each parameter specifying its data type. So in this header, the integer num declares an integer parameter named num. The header doesn't have a semicolon because it's not stopping it. It will continue to the curly braces, the body of the function. For the function call, when you call in the function, you pass an actual argument that matches the data type specified in the prototype and header. So here, val, V-A-L, is the actual argument passed to even or odd. It should be an integer to match the function's prototype and the header. The function call is also ended with semicolon. When a function is called, the value of the argument is copied into its corresponding parameter. A parameter's scope is limited to the function in which it is declared. It doesn't exist outside that function. A function can have multiple parameters separated by commas. For each parameter, there must be a corresponding data type listed in the function prototype and an argument declaration in the function header. If the argument's type doesn't exactly match the parameter's type, C++ will try to promote or demote the argument to match the parameters. The number of arguments in the function call must match the number of parameters in both the function prototype and the function definition. The first argument in the function call will be used to initialize the first parameter, the second argument for the second parameter, and so on. So you ensure that the number of arguments in the function call matches the number of parameters in the function prototype and the definition. Arguments are used to initialize parameters in the order they appear in the function call. This program demonstrates how to use a function with multiple parameters. The function prototype void showSum integer specifies that showSum will take 3 integer parameters. The program prompts the user to enter 3 integers, which are stored in value 1, value 2, and value 3. The function call showSum is then called with value 1, value 2, and value 3 as argument. Here, value 1 will initialize the first parameter, value 2 the second, and value 3 the third in showSum. We will see the function definition in the next slide. Now we have the complete picture with the definition of showSum function. The function showSum is defined to take 3 integer parameters, num1, num2, and num3. Inside the function, these parameters are summed up and the result is displayed. Each parameter, num1, num2, num3, holds one of the integer values passed as an argument during the function call main. When main calls showSum value 1, value 2, value 3, semicolon in the previous slide, the control moves to showSum function here. The values in value 1, value 2, and the value 3 are copied to num1, num2, and num3, respectively. The sum of these numbers is then displayed. So the function definition specifies what the function does, including how it uses its multiple parameters. Parameters like num1, num2, and num3 serve as placeholders for the values, the arguments you passed into the function. The function works in harmony with main, receiving values from it, performing a task. Here we sum the numbers and then display the result. When the body of the function finishes execution, the control will go back to the main function. Again, the value 1, value 2, value 3 in the function call are copied into the parameter num1, num2, and num3 in the function definition. There are 2 different types of passing data. The first type is passing data by value. When an argument is passed to a function, its value is copied into the corresponding parameter. Changes made to the parameter inside the function do not affect the original argument's value in the calling function. This is because the parameter is essentially a new variable that gets its initial value from the argument. Pass by value is useful when you want the function to work with a copy of the data, leaving the original data unchanged. So in pass by value, the argument's value is copied into a new variable, which is the parameter inside the function. Changes to the parameter do not affect the original argument. In main, we have an integer variable val with an initial value of 5. We call even or odd and we pass val. Then the value of val, which is 5, is copied into the parameter num inside even or odd function. The function can modify num. For example, we multiply it by 2. However, this change affects only num and not val. So after the function call, val remains unchanged and still holds the value 5. This is because num was a separate copy of val, and the changes to num do not affect val. Functions can be used to display menu and handle user choices, making the code more organized and easier to manage. In this function show menu, the function displays various membership options for a health club. The functions can also be designed to perform general tasks that can be reused in multiple parts of a program. Higher level functions can call these general purpose functions to perform subtasks, thereby minimizing the total number of unique functions needed. This approach speeds up program development time and enhances maintenance. The primary role of the return statement is to end the execution of a function and return control to the calling function. The return statement can be placed anywhere within the function body, not just at the end. Any statements follow a return statement within the same block will not be executed. The return statement can be used to exit a function, preventing any abnormal termination of the programs. In a void function, the return statement is optional. If omitted, the function will simply end at its last closing braces. This example demonstrates how to use a function to perform division while also gracefully handling division by zero. The function prototype void divide double double specifies that the divide will take two double parameters in the return void. The program prompts the user to enter two numbers which are stored in num1 and num2. The function divide is then called with num1 and num2 as arguments. The function divide is defined to take two double parameters, argument 1 and arg2. It returns void, meaning it doesn't return any value to the calling function. Inside the function, there's a check for division by zero using if arg2 equal 0.0. If arg2 is 0, the function outputs an error message and returns early, preventing abnormal termination. If arg2 is not 0, the function proceeds to divide arg1 by arg2 and displays the quotient. The return statement is used to exit the function early in case of an error condition, making the code more robust. A function can be designed to return a value of a specific type, which can then be stored in a variable or used in further calculations. We have a double x equal POW, then we have a 2.0 and a 10.0. Here, the POW function returns a value that is stored in the variable x. The return type of a function is specified in its signature. For example, the POW function has a return type of a double. The function sum is declared to take two integer parameters, num1 and num2, and return an integer. Inside the function, a double variable named result is declared to store the sum of num1 and num2. The return statement is used to send the value stored in result back to the calling statement. Note that there's a type mismatch in this example. The function is supposed to return an integer, but result is a double. This would lead to implicit type conversion, which may not be desirable. In value returning function, you can simplify your code by directly returning the result of an expression. This eliminates the need for a temporary variable to store the result. So in this, sum is designed to take two integer parameters num1 and num2. Instead of declaring a separate variable to store the sum, the function directly returns the result of the expression num1 plus num2. So this approach makes the code more concise and eliminates the need for an extra variable. This program demonstrates how to use a value returning function to perform a sum operation. The function prototype integer sum integer semicolon specify that the sum will take two integer parameters and return an integer. In the main function, we initialize value 1 and value 2 with the integer 20 and 40 respectively. We call the sum function and store its return value in the variable total. Finally, the program displays the sum of value 1 and value 2, which is stored in the total. The function sum is defined to take two integer parameters num1 and num2. It returns an integer which is the sum of num1 and num2. The function directly returns the result of the expression num1 plus num2, making the code concise and efficient. When main call sum value 1, value 2, semicolon, the control moves to this sum function. The values in value 1 and value 2 are copied into num1 and num2 respectively. The sum of these numbers is then returned and stored in total within main. In main, the value 1 is initialized to 20 and the value 2 is initialized to 40. So when in the main, we make a function called sum value 1, value 2, semicolon, and the 20 and the 40 will be copied into the num1 and the num2 in the sum function. And then inside the sum function, it returns num1 plus num2, and the result 60 will be returned and will be stored in the total variable. This example demonstrates how to use multiple value returning functions to calculate the area of a circle. The program used two functions, getRadius to get the radius from the user, and a square to square that radius. GetRadius takes no parameters and returns a double. Square takes a double parameter and also returns a double. In the main function, it initializes the constants and the variables, sets numerical output formatting, and then calls the two functions to calculate the area of the circle. The getRadius function prompts the user for the radius of the circle and returns it. The square function takes a double argument and returns its square. The area is calculated using the formula area equal pi multiply the square of radius, where the square of the radius is obtained by calling square radius. Again, let's say the user enters 10 as a radius. When the function calls square radius, it will go to the function. So the 10 will be copied into the number parameter, and inside the square function, it will return number multiply number. And that 100 will be returned to this function called square radius in the main function. Then this result 100 will be multiplied with pi, and the final result will be stored in the area variable. When working with value returning functions, it's important to understand how to define them and how to handle the returned value in the calling function. Both the function prototype and the function definition must indicate the data type of the returned value. The calling function should do something with the returned value. For example, you can store the returned value in a variable for later use. You can directly output the returned value. The returned value can be used in a larger expression. Functions can also return Boolean values, true or false, which can be particularly useful for decision-making in your program. Declare the return type as bool, B-O-O-L, in both the function prototype and function definition. The function body must contain one or more return statements that return either true or false. The returned Boolean value can be used in a relational expression in the calling functions. This program determines whether a given integer is even or odd. The function returns a Boolean value true or false. In the function prototype, the function isEven is declared with a return type of bool and takes an integer parameter. In the main function, the program prompts the user to enter an integer which is stored in the variable val, V-A-L. The function isEven is called with VAL as the argument. Based on the returned Boolean value, the program outputs whether the number is even or odd. Now let's look at the missing piece, the definition of isEven function, to complete our understanding of this example. In the function definition, the function isEven is defined to take an integer parameter called number. It returns a Boolean value, B-O-O-L, Boolean value, which is stored in a variable named status. Inside the function, an if statement checks whether the number is even or odd by using the module operator. If the number is even, for example, number module 2 equals 0, then the status is set to true. Otherwise, status is set to false. So the function returns the value stored in status, which will be either true or false. Understanding variable scope is crucial when working with functions. Variables defined inside a function are known as local variables. The scope of a local variable is limited to the function in which it is defined. These variables are not accessible outside of that function. Because local variables are confined with their respective functions, they are hidden from other functions. Different functions can have local variables with the same name without conflict, as each is defined to its own function. In this example, we will explore how local variables are confined to their respective functions and are not accessible from other functions. The variable num and is defined in main and initialized to 1. It's only accessible within main. The variable num is also defined in another function and initialized to 20. It is only accessible within another function. The num in main and the num in another function are two distinct variables. Each is confined to its own function and is not accessible from the other function. The program first displays the value of num from main, then calls another function to display its own num, and finally returns to main where the original num remains unchanged. Here is the program output. When the program is executing in the main function, only the variables defined within main are visible. In our example, the num variable defined in main is accessible and its value is 1. When the program execution moves to another function, the scope changes. Now only the variable defined within another function are visible. The num's variable in main becomes hidden, and the num variable in another function takes over with the value of 20. When another function finishes execution and the program returns to main, the visibility switches back. The num variable in main becomes visible again, and its value remains unchanged at 1. Local variables and parameter variables are created in memory when a function begins execution. These variables are destroyed when the function ends its execution. The period from the creation to the destruction of these variables is known as a lifetime. They exist only within the scope of the function when they are defined. Because local variables are destroyed after the function ends, any value stored in them is lost between calls to the function. Similarly to local variables, parameter variables also have a limited lifetime. They are created when the function is called and destroyed when the function ends. Global variables are another important concept in programming, especially when contrasted with local variables. A global variable is defined outside of all functions in a program. The scope of a global variable extends from the point where it is defined to the end of the program file. This means it is accessible throughout the entire program after its definition. Because of its scope, a global variable can be accessed by all functions that are defined after the global variable definition. While global variables offers the convenience of program-wide accessibility, they come with drawbacks that can make your code harder to manage and debug. Global variables can be modified by any function that can access them, making it difficult to trace changes and debug issues. They can lead to spaghetti code, where it is hard to understand the flow and the state changes. Overuse of global variables can make your code less modular and harder to maintain. It becomes challenging to understand the dependencies between different parts of your code. So if you need a variable to be accessible throughout your program, consider making it a global constant. Global constants are defined ones and cannot be changed, making them safer to use. In this example, we will see how global constants can be effectively used to make the code more maintainable and less error-prone. Pay rate, base hours, and OT multiply are defined as global constants. They are accessible throughout the program and cannot be modified. The two-function prototype getBasePay and getOvertimePay are declared. These functions will presumably use the global constant for their calculation. The local variables in main include hours, base pay, overtime, and the total pay. They are local variables defined in the main function. These variables will hold the hours worked, base pay, overtime pay, and the total pay respectively. The program prompts the user to enter the number of hours worked and stored in the hours variable. The getBasePay function is called to calculate the base pay based on the hours worked. This function uses the global constant base_hours and the pay_rate for its calculations. If the hours worked exceed base hours, the program calculates the overtime pay. The getOvertimePay function is defined later. The total pay is calculated by adding the base pay and any overtime pay. The pay details are then displayed with proper formatting. The function getOvertimePay takes a number of hours worked as an argument and returns the calculated overtime pay. If the hours worked exceed base hours, the function calculates the overtime pay. The calculation used the global constant pay rate and the OT multiplier. If the hours worked do not exceed base hours, the overtime pay is set to 0. The function returns the calculated overtime pay, which will be used in the main function to determine the total pay. Local variables are not automatically initialized. They contain garbage values until explicitly initialized by the programmer. Unlike local variables, global variables are automatically initialized. Numerical types are initialized to 0, and the character type are initialized to null and ULL. Global constant must be initialized at the time of their declaration. Local variables exist only during the function's execution. Contents are lost when the function terminates. Static local variables retain their contents between function calls. They are initialized only the first time the function is executed. Default initialization value is 0. Local variables must be explicitly initialized. Static local variables are automatically initialized to 0 if not explicitly initialized. In this example, we will see how local variables behave within a function and how they do not retain their values between function calls. The function showLocal is declared at the beginning and its definition follows later. Inside the showLocal, we have a local variable localNum initialized to 5. The main function calls showLocal twice. Each time showLocal is called, localNum is reinitialized to 5. The value 99 assigned to localNum at the end of first call is lost when the function terminates. In this example, we will explore how static local variables behave differently from regular local variables by retaining their values between function calls. The function showStatic is declared at the beginning, and its definition follows later. The main function calls showStatic 5 times in a loop. In the showStatic, we have a static local variable statNum. It is not explicitly initialized, so it defaults to 0. The main function calls showStatic 5 times. Every time showStatic is called, statNum retains its value from the previous call. The value of statNum is displayed and then incremented. Static local variables like statNum retain their values between function calls. This behavior is useful for tasks that require state retention across multiple function calls. Unlike regular local variables, static local variables are initialized only once, the first time the function is called. If you explicitly initialize a static local variable, that initialization only occurs the first time the function is called. Subsequent calls to the function will not reinitialize the static local variables. In this example, stat_num is initialized to 5 only the first time showStatic is called. On subsequent calls, stat_num retains its previous value and is not reinitialized to 5. If not explicitly initialized, a static local variable defaults to 0. A default argument is an argument that is automatically passed to a parameter if the argument is missing in the function call. This simplifies function calls and allows for more flexible code. Default arguments must be constant and are usually declared in the function prototype. In this example, if even or odd is called without an argument, 0 will be used as the default value. If there is no separate prototype, the default argument can be declared directly in the function header. Functions with multiple parameters can have default arguments for some or all of some. So in this example, the function getSum has 3 parameters, the last 2 of which have default values of 0. The function display_stars is declared with 2 parameters, both of which have default values, 10 for columns and 1 for rows. The first call to display_stars uses both default values, 10 for columns and 1 for row, and the second call to display_5 overrides the default value for columns but use the default values 1 for rows. The third call to display_stars 7,3 overrides both default values using 7 for columns and 3 for rows. This part is the actual implementation of display_stars function, which use default arguments. The function display_stars is defined with 2 parameters, cols and the rows. Both have a default value, 10 for the columns and 1 for rows. The function used the nested loops to control the number of rows and columns of asterisks to display. The outer loop down controls the number of rows. The inner loop across controls the number of columns. Inside the inner loop, an asterisk is printed for each column in the current row. After each row is printed, a new line character is added. So this function uses default arguments to provide flexibility in how it is called. Nested loops are used to control the display of asterisks based on the arguments provided or their default values. If not all parameters have default values, those without default values must be listed first in the parameter list. The correct one, integer getSum, we have 3 parameters, integer, and then default integer equals 0, and the default parameter integer equals 0. And the incorrect one is it lists the integer and the integer equals 0 and the integer equal integer. So this is wrong because those without default values must be listed first in the parameter list. If you omit an argument that has a default value in a function call, all the arguments that follow it must also be omitted. For example, sum equal get sum, num1, num2. Incorrect one is sum equal get sum, num1, then num2 is omitted, then num3. So always declare parameters without default values before those with default values. If you choose to omit an argument with a default value, you must also omit all following arguments. Pass by reference is a mechanism that allows function to work directly with the original argument from the function calls, rather than a copy. This enables the function to modify the argument's value in the calling environment. There are two reasons: to modify values in the calling environment, and also allow a function to return more than one value. In C++, you can use the AND symbol to indicate a parameter should be passed by reference. A reference variable is essentially an alias for another variable. It doesn't hold its own value. Instead, it refers to the value of the variable it is associated with. A reference variable is defined using ampersand symbol. You can use reference variable as function parameters to implement pass by reference. In this function prototype, length and width are reference variables. Any changes made to a reference variable are actually made to the variable it refers to. The program demonstrates how to use a reference variable as a function parameter. The function double_num takes a reference variable as its parameter, allowing it to modify the original argument. In the main function, the variable value is initialized to 4. The function double_num is called with value as its argument. After the function call, the program displays the modified value of value. The function double_num is defined to take a reference variable, ref var, as its parameter. The function doubles the variable stored in ref var by using the multiply equal operator. Because refval is a reference variable, this change will reflect back on the original variable that was passed as an argument. So using reference variable allows the function to modify the original argument effectively, allowing the function to return a modified value without actually using the return statement. When you call double_num value in the main function, refval becomes an alias for value. So this function modifies refval, which in turn modifies value in the main function. In the main function, the original value is 4. After call the double_num, if you see out the value, it becomes A because it is modified inside the function double_num. Each reference parameter must be declared with an ampersand. The space between the data type and the ampersand is optional. The ampersand must be used in both the function prototype and the function header to indicate that the parameter is a reference. The argument passed to a reference parameter must be a variable. Expressions or constants cannot be passed as reference arguments. Use reference parameters when you want the function to modify the original variable. Do not use them when the argument shouldn't be changed by the function. Also avoid using them if the function only needs to return a single value. In such case, a return statement is more appropriate. Function overloading allows you to define multiple functions with the same name but different parameter list. This enables you to perform similar tasks with different types or numbers of arguments. Overloading functions can make your code more readable and maintainable by using a single function name for similar tasks. It also allows you to handle different data types or numbers of arguments without having to create uniquely named functions for each case. So when an overloaded function is called, the compiler selects the appropriate version based on the numbers and the types of arguments passed. The compiler matches the function call with the correct function definition based on the argument list. If it cannot find a match, it will throw a compile time error. We have 4 overloaded versions of the function getDimensions. The compiler selects the appropriate version of getDimensions based on the types and the number of arguments passed in the function call. Each function call here corresponds to a different version of getDimensions as indicated. So overload function allow for more flexible code by enabling the same function name to handle different types or numbers of parameters. The compiler automatically selects the appropriate version of the function based on the arguments provided in the function call. This example demonstrates how to use overloaded functions to handle different data types, especially integer and double. The 2 versions of the function square are declared. One takes an integer parameter and the other takes double. The program asks the user to input an integer, user int, and a floating point number, user float. The square function is called twice, once with an integer argument and once with a double argument. The compiler automatically selects the appropriate versions of square based on the type of argument passed. In this slide, we look at the implementation of the overloaded square functions that work with both integer and double data type. The version of square takes an integer argument and returns its square as an integer. This version takes a double precision floating point number and returns its square as a double. Although both functions have the same name, their parameter types differ, makes them unique in the eyes of the compiler. So when you call square, the compiler will automatically select the appropriate version based on the type of the argument you pass. The exit function is used to terminate the execution of a program immediately. It's a part of a CS2250 header file. Exit can be called from any function, not just a main function. The exit function can pass an integer value back to the operating system to indicate the status of the program termination. Typically, exit 0 indicates successful termination, while other values indicate various types of errors. While it's common to return controls to the operating system by simply allowing main to return, the exit function is often used for abnormal termination scenarios, such as error conditions that make it impossible for the program to continue executing. To use the exit function, you need to include the CS2250 header file. The exit function can be used to predefine constants to indicate the success or failure of a program. So exit 0, this is a simple example where 0 is passed to indicate successful termination. Exit underscore success and exit underscore failure. So exit success and exit failure are constants defined in the CSTD lib header. So exit success is typically equivalent to 0 and indicates successful termination. Exit failure is used to indicate that the program has terminated due to some error or failure. So using this constant makes the code more readable and allows you to understand the termination status at a glance. A stub is a placeholder function that mimics the behavior of a real function you plan to implement later. It is often used when you want to test a part of your program that calls a function you haven't written yet. For example, a stub might simply print a message saying function X called and may display the parameters it received. A driver is a function that calls another function for testing purpose. It passes various arguments to the function under test and may check the return values to ensure they are as expected. Subs and drivers allow you to test parts of the program in isolation, which is useful for debugging and ensures that each component is working as expected before integrating them.